In this video, we're going to look at quantum logic, and specifically we're going to examine the NOT gate. So let's draw out our quantum system again in terms of energy levels. So we have, it's a two-level system. So our ground state is n equals 1. Electron volts are here on the vertical axis, and then we have our n equals 2, which is our first excited state. Now, a quantum computer relies on reversible computing, which means you can never lose a state. Traditionally, in a classical computer, there's four things that you can do with the bit. There's identity. So what is the bit? There's the NOT gate, so you can invert it. There's set to 0 and set to 1. In a quantum system, you can never set anything to a 1 or 0 because essentially you've lost the state, the previous state. So the only two operations that we can do is identity and NOT. Identity is self-explanatory, but here's the NOT gate. So diagrammatically, a NOT gate would look like this. An X in the middle. And so we would define that, and that is our quantum bit. So at this point here, we are in the ground state, or our spin down condition. So let's draw it out on the unitary circle. And in ket notation, we have a state like that. So when we execute the NOT gate, we're going to actually, in real life, fire some electromagnetic energy at our quantum system, and it's going to be of a specific frequency. Energy level 2 minus energy level 1, the ground state, over Planck's constant, as was discussed before. And when this gate is executed, the electron will jump up to its next energy level, and the magnetic moment, or the poles, will be reversed, and this will be now the spin up condition, and this is the spin down condition. And we would see on our unitary circle, the vector has moved from this position, which is the one in vector notation 1, 0, and we've moved up to this position, which we call the 1 state, and this is a vector condition of 0, 1. Each gate is actually represented in quantum computing by some linear algebra. So the NOT gate is a matrices of 0, 1, 1, 0. So if we have our ground state here represented by 1, 0, and then we do our matrix operation on that, so that equals 0 times 1 is 0, 1 times 0 is 0, and then 1 times 1 is 1, plus 0 times 0 is 0, and we end up with this vector, which corresponds to our spin-up state and what we've defined in our ket notation as our logical one. So each gate, and as we go to explore different types of quantum gates, is really a function of what kind of frequency we're firing at our quantum system. We represent it by a matrix. We do a little bit of matrix math here, and we get the output of the change. And the unitary circle is very useful actually, because it's essentially the state machine of our system. So the NOT gate has rotated our vector 90 degrees because they're orthogonal, the spins. And as we go on to show different types of gates, you can see we'll explore more on the unitary circle of where the vectors are going to transition to with different gates or different combinations of gates.